The world is filled with light. The scenes around us reach our eyes as a result of light. Lenses receive that light and convert it into images. With 70 years of lens-making experience, Canon continues to pursue the ideal lens. A lens gathers light and projects it onto a screen. This is the fundamental principle of cameras that use lenses. Light that hits the lens's optic axis in a parallel line is refracted by a convex lens and brought together into a single point. This is the focal point. Why is an image created when light passes through the lens? Light transmitted from a single point on a flower passes through the lens and meets at a single point. Light transmitted from other points is concentrated in the same way, creating an image. In reality, however, the image created by a single convex lens is indistinct. The clear, distinct images achieved by cameras are only made possible as a result of wide-ranging knowledge of and experience with lenses. Lenses are made of glass, but normally glass is colored due to impurities. Take blue glass, for example. Light is made up of three primary colors: red, blue, and green. When the red light and green light are absorbed by impurities in the glass, a larger percentage of the light passing through is blue. This is why the glass appears blue. Optical glass is created when the impurities are successfully removed. During the manufacturing process, cracks or irregularities called stria sometimes appear. Only glass free of such irregularities is used as optical glass. The ideal lens is one in which incoming light meets at a single point. In the past, a variety of spherical lenses cut from the surface of a sphere were used to accomplish this. With spherical lenses, however, the incoming light doesn't meet at a single point. It is spread out slightly. This is known as spherical aberration. The position of the focal point for the light that passes through the center of the lens and the light that passes through surrounding areas does not line up. This misalignment causes the image to become blurred. Spherical lenses are also subject to other types of aberrations, such as distortion. There is also the problem of chromatic aberration. A rainbow is formed when the light passing through water droplets is refracted. Different refraction wavelengths cause the different colors of the rainbow. This same principle causes chromatic aberration in lenses. The focal point for blue light, which has a short wavelength, is closer than that for red light, which has a long wavelength. This causes the colors to bleed. As such, a number of difficult problems arise when spherical lenses are used as camera lenses. Canon's ideal lens is one that projects focus points as true points, free of blurred images, distortion, and color bleeding. To achieve this goal, Canon has been working to solve the problem of aberrations. The first step toward correcting aberrations is to combine lenses with different characteristics, such as convex and concave lenses. Spherical aberration occurs in opposite directions in the case of convex and concave lenses, so aberrations can be corrected by combining these two lens types. Chromatic aberration can also be corrected by combining convex and concave lenses. Moreover, by joining lenses made of different materials, it is even possible to correct chromatic aberration without changing the position of the focal point. Canon has found a revolutionary way to solve the problem of spherical aberration. The solution is an aspherical lens, which is not affected by aberrations on the lens surface. Canon succeeded in the very difficult task of designing and producing aspherical lenses, and in the process, increased quality while reducing the number of lenses needed. Aspherical lenses also contribute to the correction of distortion. Fluorite has gained attention as an ideal lens material because it is not susceptible to chromatic aberration, but there are problems with practical applications in terms of purity and size. Canon, however, succeeded in artificially creating large, high-purity crystals and has already begun to mass-produce fluorite lenses. We have also successfully commercialized Super UD lenses, which have optical characteristics similar to fluorite. In addition, Canon has also developed a revolutionary DO lens using diffractive optical elements. By creating a diffraction lattice, which was once considered impossible, Canon developed a DO lens that generates chromatic aberration in perfect contrast to convex lenses. Chromatic aberration can thus be corrected by pairing a DO lens with a conventional lens. Canon's pursuit of the ideal lens has enabled us to overcome various aberrations that were thought to be insurmountable. When designing lenses, Canon uses original computer software that incorporates our years of accumulated know-how to discover the optimum lens configurations and positions to minimize all aberrations. There's one more important technology needed to achieve the ideal lens. That's manufacturing technology. Manufacturing technologies and know-how refined over many years enable these lenses to perform the way they were designed to. Cutting-edge optical technologies are supported by the skills of master craftsmen who uphold a long tradition of quality. Master craftsmen polish lenses with polishing plates, which they calibrate by hand with nanometer accuracy. Countless layers of coating are applied to the lens surface to prevent reflection and flare and to increase light transmission. This is how interchangeable lenses embodying all of Canon's know-how are born. The correction of chromatic aberration using UD and fluorite lenses has increased the image quality of super telephoto lenses. The distortion correction achieved by aspherical lenses has made possible the development of super wide-angle lenses. Medium telephoto lenses using large aperture aspherical lenses have dramatically improved photographic performance. Combining advanced design technologies with manufacturing technologies cultivated over many years, Canon continues its pursuit of the ideal lens.